All right, now we're starting on chapter 10, where we're going to build up to power series, and we're going to use what you learned in chapter 9 to check for intervals of convergence. To start with, but we have to start, before we can do power series, we have to start with approximating functions with polynomials. And you've already done this when we did tangent line approximations. So just let me draw you a sketch. Suppose you have some function f of x. And you have some point. This is a, this is f, the function at a, so it's the y value. And you're going to write a tangent line. And we know from tangent lines that at this point, a f of a, the point is it's the same point on both the function and on the tangent line. We'll call this tangent line, we'll call it polynomial order 1 x. And at that point, the function value is equal to the polynomial value, which is our line, and the derivative of the function is equal to the derivative of the polynomial approximation. And y minus the function value is equal to f prime of a times x minus a. That's what we did with our tangent line approximations. We're going to call this now, instead of y, it's the polynomial first order, is equal to f of a plus the derivative at a of the function times x minus a. And actually, I'm just going to slide this over so that I have a little more room here. X minus a. There we go. All right. Well, that's a first order approximation. We're going to do higher order approximations. So let's assume that now we're going to take the function and suppose instead of, so here's our f of x, and instead of doing a tangent line approximation of a line, we do a tangent line approximation of a, here's our point, this is a, this is f of a, and I'm going to do an approximation this time with a polynomial, in this case with a quadratic. So the quadratic and the line share that point. So that point there is a f of a, and that's the point on both. So this is p second order. It's a second order approximation. So in this case, our second order approximation is equal to, and well, let's look at it. So the point at a is f of a, well actually, let me write this. So in green, this is the second order a, but on the function at a, it's f of a. And f of a equals p second order of a. The first derivative at a equals the first derivative of the second order polynomial at a. And the second derivative of the function is equal to the second derivative of the second order approximation. Well, that means that when we go to write the polynomial, second order polynomial is f of a, which is the value of the function, plus the first derivative of a times x minus a to the 1 power over 1 factorial plus the second derivative at a of x minus a squared over 2 factorial. And it matches up to the line. The whole point of the line is, since it's the first order polynomial, I forgot to put the 1 there. First order polynomial, it's the, come on, first order polynomial. Notice it's f of a plus the first derivative of a, x minus a to the 1 power over 1 factorial. Then for the second order approximation, you add on the second derivative times x minus a squared over 2 factorial. And we can do an nth order polynomial. And basically what goes on is, you see how with the line it's a good approximation. You have to be really, really close. With a quadratic, it's closer. It's a better approximation. It doesn't deviate as quickly. And basically what it boils down to is the higher order the polynomial, the more derivatives you take, the higher order approximation you do, the closer the approximation will be, and it is better over a larger interval. So if we're going to do, and this is called a Taylor polynomial. Getting used to writing with my surface again. I got it going again. Okay, for a Taylor polynomial, it's an nth order. And the nth is telling you the number of derivatives. Centered at x equal to a. Okay, so when you're talking about Taylor polynomial, that you're going to tell you, they have to tell you what order it is and where it's centered, and then after that, the function has to have in derivatives. At x equal to a. Or you can't do an nth order derivative. You can only do the nth order polynomial for the number of derivatives that are possible for the function you're given. So the way we write it, this is Taylor polynomial at x of x is a function of x is equal to the Taylor to just another way to do it. We just call it a polynomial, and we say that it is equal to the function evaluated at a, the center point, plus the first derivative evaluated at a times x minus a to the 1 power over 1 factorial. I won't write the 1. And then that's plus the second derivative at a times x minus a squared over 2 factorial. And then it's plus the third derivative at a times x minus a cubed over 3 factorial plus dot 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 plus the nth order, so f nth derivative at a times x minus a to the nth power over n factorial. And if you do this, if you add enough terms, and that's where we get into the is it a good enough approximation? If you add enough terms, you can approximate a function to a certain error, and we'll figure out how to do that later. But it's basically you want to do enough derivatives in order to get your approximation close enough. And this is the nth order. Okay. So it's nth order derivative and nth degree. Nth order derivative. Oh, actually, let me rewrite that. We'll set over here. this is the nth order derivative. And this is the nth degree polynomial. All right. Now, there's another approximation, very similar to this. Okay, it's a Maclaurin polynomial. Oops, oh well. It's very similar to the Taylor, but it's a special case of the Taylor. In the Maclaurin polynomial, it's the same as the Taylor, but it's a special case of when a is equal to 0, meaning you are centering your approximation at x equal to 0. So it's all right for the Maclaurin series. It's just the polynomial, the nth order polynomial or nth degree polynomial is equal to f evaluated at 0 plus the derivative, first derivative at 0, x minus 0, so it's just x over 1 factorial plus the second derivative at 0, and it's x squared over 2 factorial plus the third derivative at 0, x cubed over 3 factorial plus dot 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 plus the nth order derivative evaluated at 0 times x to the nth power, which means it's the nth degree polynomial over n factorial. Okay, so what does that look like when you do a problem? And they do. This will be on the AP test. You have multiple choice problems. You will have free response problems. So example 1, you're going to find the polynomial for a fourth order approximation of e to the 2x centered at a equal to 0. So in actuality, what we're not doing it, we're doing this is a Maclaurin polynomial. We don't have to necessarily name it, but and we're going to use the polynomial to find e to the 0.2. We're going to approximate it. All right, so the way this works is we start off, we go f of x. What's f of x equal? F of x equals e to the 2x. And then we need the first derivative, and that's 2 e to the 2x. And then there's the second derivative, which is 4 e to the 2x. And then there's the third derivative, which equals 8 e to the 2x. And then there is the fourth derivative. And at that point, you just start using numbers. And that's 16 e to the 2x. And then we have to evaluate them. So we need f of 0. Well, that equals 1 because anything to the 0 power is 1. And f prime of 0 is going to equal 2 because e to the 0 is 1. And f double prime of 0 is equal to 4. And the third derivative at 0 is 8. And then the fourth derivative at 0 equals 16. All right, now we're going to build our polynomial. So I'm going to go to another page. All right, so to write our polynomial, we just go, okay, the polynomial is fourth degree. Actually, it's just, we're starting with the fourth order derivative. So it's going to be 1, which is our first term, plus our second derivative, our first derivative at 0 is 2 times x minus 0, right, over 1 factorial. And it's 1, and we don't need to show that anymore, right? So then our second derivative is 4 times x squared over 2 factorial, which is 2, plus our third derivative is 8x cubed over 3 factorial, which is 6, plus 16x to the fourth over 4 factorial, which is 24. And then we would simplify this. This becomes 2. This becomes 4/3. That becomes 8. And our polynomial is a fourth degree polynomial because I have the x, that tells me the degree. It's fourth degree. And I did a fourth order derivative. Those don't always match, and we'll talk about that later. So this equals 1 plus 2x plus 2x squared plus 4/3 x cubed plus 2. Oh wait, that was 24. That wasn't 2. So 16, you're going to factor 8 out. This is 2/3. 2/3 x to the fourth. So that is our fourth degree polynomial. So if we want to find or approximate e to the 0.2, e to the 0.2 is approximately, that's equal to, actually it is equal to, that's equal to e to the 2 times 0.1, right? Which means that in our case, because remember it started out was 2x, back to our example, we were approximating 2e to the 2x, so that means that x in our case is going to equal 0.1. So e to the 0.2 is approximately the fourth degree polynomial evaluated at 0.1, which would be 1 plus 0.2 plus 2 times 0.1 squared plus 4/3 times 0.1 cubed plus 2/3, 0.1 to the fourth. And when you add that all up, it's approximately 1.2214. If you plug that into the calculator, e to the 0.2 is about 1.2214027 28 dot. This is in the calculator. Look how good this approximation is. This approximation is good to 4 decimals, and we only had 4 terms. That's pretty good. All right, for our next trick, we're going to try something a little more interesting. It's going to be centered somewhere. It's not going to be centered at 0. So this is 10, 1. Example 2. Okay. And for this time we're going to find, oops, no more red. Find the just say the polynomial. They won't tell you specifically. They'll just say find the polynomial. Of degree n equal to 6 for ln of x at a equal to 1. All right. So what is that telling us? Well, the degree of the polynomial, when they're telling us that that's telling us that that is a polynomial with an x to the 6th term. And then this, at a equal 1, that means it's centered at at x equal 1. All right, so we're going to do the same procedure. It's essentially the same procedure. So for f of x, that's natural log of x. And I need 6 derivatives this time. So I need the first derivative, the second derivative, the third derivative, the fourth derivative, the fifth derivative, and the 6th derivative. All right. So for natural log of x, its derivative is 1 over x, which is x to the negative 1. The second derivative is negative x to the negative 2, which is negative 1 over x squared. The third derivative is 2x to the negative 3, which is 2 over x cubed. The fourth derivative is negative 6x to the negative 4, which is negative 6 divided by x to the 4th. My fifth derivative is 24x to the negative 5, which means it's 24 over x to the 5th. And my sixth derivative is a negative 120 x to the negative 6, and that equals negative 120 over x to the 6th. And that's not that hard. Now we have to evaluate it at 1. So we want f of 1, well, natural log of 1 is equal to 0. It's the x-intercept for that. That's the point on all the logs. That's the x-intercept for all the parent function for logs. And then I need the first derivative at 1. Well, that's 1 over 1. That's just 1. And then the second derivative at 1 is negative 1 over 1, so it's negative 1. And my third derivative, evaluated at 1, is 2 over 1, which is just 2. And I'm going to show you, I'll just say this, I'll go ahead and tell you, it's 2 factorial. All right, and this is 1 factorial, but then it gets interesting. So notice I've got the fourth derivative at 1 is equal to 6 over, or it's negative 6, so that's negative 3 factorial. And then the fifth derivative evaluated at 1 is equal to 24, so it's positive 24, so it's 4. 4 factorial. And then the sixth derivative, evaluated at 1, is negative 120, which is negative 5 factorial. So you have to know your factorials so that you can recognize this pattern, because then we're going to start writing it. You'll see what I'm talking about. So now we're going to write this Taylor polynomial, because it is definitely a Taylor polynomial since it's not centered at 0. And it equals 0 plus 1 minus x minus 1 to the, it's squared over 2 factorial. And then, because remember, the formula is, it's the f of a, which that's what f of 1, and then it's first derivative. I forgot. I'm sorry, yawning. I forgot something. I forgot the first derivative is times, I forgot the formula. Hang on. Let's get rid of this. So this is times x minus 1 to the 1 power over 1. And then this is minus all this mess that I moved away. I lost my 2, but that's okay. Squared. And then that's going to be plus, where was I? Oh, that's 2. Oh, that's 1. That's right. And then okay. So that coefficient was a negative 1. And then we've got 2 factorial times x minus 1 to the 3rd power over 3 factorial plus, actually I'm just going to go down here, plus, and then it's 3 factorial times x minus 1 to the 4th power over 4 factorial minus, this is 5 factorial times x minus 1, hang on, oh this is 4 factorial, I gotta hit myself, 4 factorial, 3, no, 5 over 5 factorial plus, this was minus right here because of that minus there, and then it's plus, that was plus, this one's minus, minus 5 factorial times x minus 1 to the 6th power over 6 factorial. And there's things you can do to simplify. We've played with the factorials a little bit. Remember we did that before we started all this? And notice, when you cross this out, that 2 factorial, this is just going to become 3. 3 factorial, that cancels out the 3 factorial, you're left with 4. This is left with 5. This is left with 6. And when you simplify this Taylor polynomial, 6th degree, is going to be x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4 plus x minus 1 to the 5th over 5 minus x minus 1 to the 6th over 6. Well, that works ever so nicely. And that's what our goal is. Our goal is to go ahead and get the Taylor approximations. But then the other goal is to figure out, okay, after we do that, after we've done that, what's the remainder? I mean, when we don't get the rest of those terms, how bad is our error? Well, in order to do that, we need the remainder theorem. Okay, the remainder theorem for Taylor polynomials is basically that for any f of x, we're approximating f of x, and we're going to say it's the polynomial to the nth order, whatever we do, right? Suppose we do the sixth order, and then it's going to be plus the remainder, r sub n. Just like on the other, we've chopped off, and that's the tail left over. And that remainder, the tail we chopped off, is less than or equal to the function, and it is the nth plus 1 derivative. It's acting weird. Stop. Plus 1. Evaluate at some value c, and then it's x minus 1 times n plus 1, and that's the center. We're writing this at 1, so I'm writing this specifically for this example, over n plus 1 factorial. Take the absolute value of that, and in this case c is somewhere between x and a. And if I write this right, this is a right here. This is a. I'm doing a specific example. And then a I look at my remainder term again. But anyway, we got to do if it's the positive case, if it's the negative case, then it's the other way around. A is less than C is less than X. Those are your choices. Basically, C is between X and A, because you can have it on the other side. If you had written X plus A, it would have been the other way around. So we're going to finish up number 2. We're going to do that example. Now that we've got this, we're going to find, so this is part B for our example. For example 2. And it's going to be find hang on. Yeah, okay. So we're going to find third order Taylor polynomial for f of x equal to ln of x, centered at x equal to a, centered at a equals 1. And we're going to approximate f of 1.2. And then in part B of this one, so that's A, part B, we're going to find the remainder So we're using those same terms we did before. We're just going to be using these. We're just going to use those. Only we're going to write it for third order and then figure out what happens. And the reason we're doing third order is because now if I do third order, then I have the fourth order right there to be able to write it all up. So if we just write a third order, so this is part A, we have the Taylor third order or third degree. In this case, it's the same difference. It equals the x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 All right. And if we want to approximate natural log of 1.2 with this Taylor third degree polynomial, it is going to equal, well, 1 minus 1.2 is going to be, actually 1.2 minus 1 is 0.2. And then minus 1.2 minus 1 is 0.2 squared over 2 plus 0.2 cubed over 3. And that equals 0.1827. Now, when I wrote this remainder theorem, the thing is, what the heck is this C thing? Well, what C is the maximum. This is this thing. That's the maximum value of f, the n plus 1 derivative where it's between, where the C is between x and a, so it either can be, depending on which side of the A you're on, it's either that or that. It's either if it's to the left or the right. So in our case, we're looking for it to be between 1 and 1.2. So I need another page. And I'll write down what it is in a second. So what we're looking for is, so we've got our remainder, third order or degree, is less than or equal to f fourth derivative, because we got it wrote to 3, of C, where that's going to be, it's the maximum for the interval from 1 to C to 1.2. If on the other hand we had said it could have been the interval from 0.8 to 1 instead. But anyway, so, and then it's going to be times 1.2 minus 1 to the 4th power over 4 factorial. And we want the absolute value of this. Because if we were looking at the interval from 0.8 to 1, it would end up being negative. Well, not this case. If we did a 5th order, it would be, no. If we did a 4th order, it would be negative. In any case, you're going to take the absolute value of it. And from above, the 4th derivative of x was, wasn't it, yeah, negative 6 x to the 4th, so it's negative 6 x to the negative 4. And we've got to figure out for this where its maximum is. So we're going to take this 5th derivative, and we already have that, right? We have the 5th derivative, and the 5th derivative was 24 x to the negative 5. And that is positive. It's greater than 0. Since it's positive, it is telling me, that tells me that this tells me that the 4th derivative is increasing. Since it's increasing, the maximum is going to occur at the, so maximum occurs at the right side, the right side of the interval. Which means that it's going to be maximum is at f fourth derivative of 1.2. Okay, so that, and what a lot of times instead of writing this, they'll just write an m. They'll write m there for maximum. And you just have to know it's the n plus 1 derivative. So the maximum, that m, is equal to f fourth derivative at 1.2, which equals negative 6 over 1.2 to the fourth power. So our remainder for our third degree polynomial is less than or equal to the absolute value of negative 6 over 1.2 to the fourth power times 1.2 minus 1 to the fourth power over 4 factorial, and that is equal to 0.000193. And what does that mean? That means that our error is bounded, so that we know that from negative 0.000193, the actual function value at 1.2 minus the Taylor polynomial evaluated at 1.2 there we go. Okay, so it means we've bounded our error. We've bounded our approximation. And the Taylor polynomial was 0 point, so we're going to add 0.1827 we got for our approximation. And that means that the approximation, the actual value of the function evaluated at 1.2 is between 0.1825 and 0.1829. So we have bounded our actual value. And that's ultimately where we want to get to. But it's going to take some practice. First, we have to be able to write Taylor polynomials. Then once we can write Taylor polynomials, then we can start playing around with the error. And eventually you will be able to figure out how many terms we need. And I think that's enough for one day.